Welcome back to The Explainer. Today, we are looking at a truly fascinating piece of scientific research that honestly reads a lot like a superhero origin story. We're going to explore how scientists are taking one of nature's absolute biggest nuisances, an invasive aquatic plant known as the water hyacinth, and completely engineering it into a high-tech, magnetic sponge designed to fight a massive industrial villain, heavy metal pollution. It's a textbook example of turning a major environmental headache into an incredibly elegant solution.
Okay, let's dive right into our roadmap for today. We'll be hitting 6 key areas: the toxic tannery problem, building a magnetic nanocomposite, a quick comparison of pristine biochar versus the nanocomposite, the chemical mechanisms of chromium adsorption, the Box-Benkin optimization, and finally, a real-world tannery wastewater test.
Starting off with Section 1, the toxic tannery problem.
So, how exactly can an invasive aquatic weed solve one of the textile industry's most toxic problems? You've probably heard of water hyacinths. They're notorious for clogging up waterways, blocking out sunlight, and just completely disrupting local ecosystems. But, that nuisance really pales in comparison to the severe threat of industrial heavy metal pollution pouring out of factories that make our everyday leather goods and textiles. So today's researchers asked a pretty brilliant question. Can we use the weed to defeat the waste?
The specific villain we're dealing with here is hexavalent chromium, or CRVI for short. This is a highly reactive, water-soluble, and extremely toxic transition metal compound. Because it dissolves so easily in water, if it's discharged from a tannery without proper treatment, it rapidly enters our local water supply and eventually the food chain. It's non-degradable, highly toxic, and in chronic cases can even cause cancer. Traditional water treatment methods, they often struggle to eliminate this specific compound efficiently or cost-effectively. So that is the final boss our engineered biochar needs to defeat.
Let's move to Section 2, building a magnetic nanocomposite.
Now, what's really interesting about this is the fabrication process. The scientists don't just use the raw plant. First, they take the dried water hyacinth stems, crush them up, and pyrolyze them at 450 degrees Celsius in an oxygen-limited environment. That creates a basic biochar. But they don't stop there. To make this thing a true pollution-fighting powerhouse, they mix this biochar in a solution with functionalized carbon nanotubes, or CNTs, and a very special ingredient, cobalt, zinc, ferrite nanoparticles. After some heating, washing, and drying, you get the final leveled-up product, the CNT-CZB nanocomposite. Now, you might be wondering, why go through the trouble of adding cobalt, zinc, ferrite? Well, it essentially acts as built-in handles. See, one of the biggest problems with using powdered biochar to clean water is that once it absorbs all those toxins, it's incredibly difficult to fish that powder back out of the water. If you can't get it out, you just cause secondary pollution. But by incorporating that co-ZN spinwell ferrite, the researchers made the entire nanocomposite magnetic. This means once the biochar is completely full of toxic chromium, you can literally just pull it out of the wastewater with a magnet. It's an incredibly elegant solution to a very messy problem.
All right, Section 3, pristine biochar versus the nanocomposite.
Let's look at the stats. Before the upgrade, the pristine water hyacinth biochar had a surface area of about 35.6 square meters per gram, with an average pore diameter of 35.15 nanometers. But after the carbon nanotubes and ferrite were added, the surface area more than doubled to nearly 76 square meters per gram. Meanwhile, the pore diameter actually shrank down to 20.4 nanometers. So what's the crucial takeaway here? Why does a smaller pore size even matter? It's because 20.4 nanometers keeps those pores squarely in the mesoporous range. That happens to be the exact perfect size for chromium ions to slip inside and get permanently trapped, while the massive increase in surface area means there are just far more sites for those ions to get stuck on. And this brilliantly illustrates the radical physical transformation we're talking about. While the pristine biochar has some, irregular cracks here and there, the nanocomposite looks entirely different. Because carbon nanotubes are tubular and fibrous, they adhere to the biochar and create this incredibly dense, rough 3D porous network. It essentially turns a slightly porous piece of burnt plant matter into a massive microscopic supersponge.
Which brings us to Section 4, mechanisms of chromium adsorption. Let's talk chemical superpowers. The primary mechanism at play here is called surface complexation. To visualize this, I want you to think of the carbon nanotubes as being covered in tiny chemical grappling hooks. During the fabrication process, the carbon nanotubes were treated with acids, which introduced oxygen-containing functional groups, like carboxyl and hydroxyl groups, right onto their surfaces. When the toxic chromium ions flow by, these functional groups chemically lock onto the metal ions, grappling them and binding them directly to the surface of the nanocomposite, so there is absolutely no way they can escape back into the water.
But here's where it gets really amazing. The XPS spectra data proves the material's ultimate superpower. The biochar doesn't just trap the toxic hexavalent chromium, it actually fights back. Through an electron transfer process involving those exact same functional groups, the nanocomposite literally forces the highly toxic CrVi to drop an electron, converting it into Cr3. Now, Cr3 is a much safer, significantly less toxic state. In fact, the data shows that over 61.8% of the trapped chromium is reduced to this safer state. Talk about a game changer.
There's one more mechanism we absolutely need to highlight, and that's electrostatic attraction. The researchers found this material is highly effective at a very specific acidity level, specifically a pH of 2. Under these highly acidic conditions, the surface of the biochar becomes heavily protonated, giving it a very strong positive charge. The toxic chromium floating in the water naturally carries a negative charge, so at pH 2, the biochar magnetically draws in the toxic chromium like a microscopic tractor beam.
Moving right along to Section 5, the Box-Benkin optimization.
To find out how to maximize this entire process, scientists used a really clever statistical tool called the Box-Benkin design. Think of it kind of like trying to find the absolute perfect recipe by tweaking the ingredients simultaneously rather than baking 100 different cakes one by one. They tested 3 main variables: the initial chromium concentration, the solution's pH, and the reaction time. So the crucial point the model revealed is that while all 3 matter, the initial concentration of chromium actually has the most dominant controlling effect on just how much chromium the biochar can ultimately absorb.
And finally, Section 6, the real-world tannery wastewater test.
The ultimate boss fight. The result, a staggering 101 milligrams per gram. Get this, during their perfectly controlled synthetic lab water tests, the nanocomposite achieved a maximum adsorption capacity of about 81 milligrams per gram. But when they took it out of the lab and dumped it into actual native tannery wastewater without any dilution, just raw effluent, its capacity jumped to roughly 101 milligrams per gram. It actually outperformed the synthetic tests. I mean, no way, right? This proves that this magnetic nanocomposite isn't just some theoretical lab curiosity, it is a highly viable real-world champion for industrial wastewater treatment.
Which brings us to a final, provocative thought. We just walked through how scientists took the water hyacinth, a highly problematic, invasive plant that literally chokes our ecosystems, and completely transformed it into a magnetic, chromium-destroying super sponge. It makes you wonder, as we look around at other eco-nuisances hiding in plain sight, what other invasive, problematic species are just waiting to be engineered into our next great environmental solution? It's a totally fascinating paradigm shift in how we view the weeds of the world. Thank you so much for joining me on this explainer, and hey, keep your eyes open for the hidden potential all around us.